All right, we're gonna start this. We're gonna start this video with a quick cat check-in. October is ready to learn. Hopefully, you are ready to learn as well. We're gonna do some more about sampling distributions. Oh, that's a big October, and we're gonna do an example. Okay, so a person's measured glucose level 1 hour after ingesting a sugary drink varies according to a normal model. Has some mean of concentration for glucose and some standard deviation for concentration of glucose. So what we're curious about is, again, we're going to model what we did before. Up here is the distribution, the probability for a single reading. And then if we're curious about probabilities for multiple readings, that's going to have to do with means. So before we really get into this new example, let's talk about how we can actually approximate this normal model. I said under certain conditions, independence, randomization, and sample size, under certain conditions, we can model these averages with a normal distribution. Okay, these were the conditions up here with the CLT. And here's what the model actually looks like. So when we draw a random sample from a population, if the population, so the single watermelon, the single glucose reading, if that population has a mean and a standard deviation, then the sampling distribution, the 25 watermelons or the 3 glucose measurements, is randomly, normally distributed with this mean. So this says the mean of the sampling distribution, the mean of the sample. That's what this subscript means. Mu means mean. And this subscript means it's the mean of the sample mean, which I know. It's kind of weird. The means will be the same. We saw that, right? If I had, we could even do it with the skewed, right? Notice that the mean of the population was 8. The mean of our sampling distribution with a big enough sample size was also 8. The sampling distribution, which is all the averages from our samples of 25 in this case, has the same mean as the parent population. This blue line is in the same spot. All right, that's what this says. Over here, this says the standard deviation of the sample. The standard deviation of the sample, how spread out the sample is going to be based on the standard deviation of the population, but divided by the square root of the sample size. We can really clearly see this here. What's the square root of our sample size here? The square root of our sample size is 25. The square root of 25 is 5. So what this formula is telling us that if the CLT is satisfied, independence, randomization, and sample size, the standard deviation for our sampling distribution will be the old one divided by the square root of the sample size. This standard deviation should be this red standard deviation divided by 5, because 5 is the square root of 25. This divided by 5 is that. We could see it even better with the original watermelon example. This is our original standard deviation. Divide this by the square root of 25. What do you get? You get 1. Okay. So this shows the randomness. This is our sampling distribution for those watermelons. If I take 20, and we can use this graph, right? We can use this graph to say, okay, here's the likelihood if I look at one watermelon, what we think one watermelon will be. It'll be on average 16 pounds, but we might, get something way up here or way down here, but less likely. If we take a sample of those watermelons, a sample of 25 watermelons, we should expect on average that sample to have an average weight of 16 pounds still. But even though for one watermelon it was possible, but unlikely to be like 25 pounds, it's almost impossible to take a sample of 25 watermelons and have them average 25 pounds. It's even really rare to have a sample of 25 watermelons and have them average like 19 pounds. Okay? For this watermelon example. In real life, yeah, 19-pound watermelon is much more normal. All right, and that's what we're doing here. That's how we can model these averages. Another way of writing it is the sampling distribution, which is just how the samples are distributed. What's the randomness look like for taking a sample mean? So X bar, our sample mean, will be normally distributed with this mean and this standard deviation. Let's use that in an example. So we're done with watermelons. We're going to talk about glucose levels. Okay. We do a measurement an hour after ingesting a drink. We expect that measurement to have this average and this standard deviation for concentration. So if a single glucose measurement is made, that's like our population. That's like looking at a single watermelon. Define and draw the distribution. Well, we're told that. Okay, if we look at a single one, it's normally distributed with this mean and this standard deviation. So let X equal the glucose level 1 hour after the drink. We have been told by this problem that X is normally distributed with an average of 125 milligrams per deciliter and a standard deviation or a spread of 10 milligrams per deciliter. Just like in Unit 5, right? And we can draw a picture for this, right? We know this is what normal distributions look like. The mean is going to be in the middle. One standard deviation is about where the curve changes, so that'll be 135. Another standard deviation is 145, and everything that we know about normal distributions applies here. 68% is within one standard deviation, 95% is within two standard deviations, and 99.7% is within 3 standard deviations. Okay? That's what it wants us to do. This is old news. Parts B, C, and D and E is new news. So, if measurements are made on 3 different occasions and the mean, the average, is computed, what conditions do we have to use so that we can use a sampling distribution? Well, if we're looking at multiple and looking at the averages, that's what sampling distributions are. Sampling distributions of means, anyway. And okay, if we're looking at 1, don't need to do anything. 1 is just this normal distribution. But if we're looking at the average, just like here we looked at the average of 25, here we looked at the average of 2, well, the conditions required for it to be normal are these 3 from the central limit theorem. We need independence, randomization, and the sample size condition. All right. The sample size condition is easy here. Sample size condition said, if the population is normal, no sample size is required. Is our population normal here? Otherwise, we have a problem. Right? This is our N. I said a good rule of thumb is at least 30. But if your population's normal, you don't need a sample size requirement. And we know the population, we just talked about it up here. The population is normal here. Okay, population is normal. So none required. We don't need a sample size condition. We got it. Are these measurements independent of each other? Are they randomized? It's not really clear. We're just going to assume yes. All right, in general, I'll try to be very clear about when you can assume these or not. You can always ask me if you have questions too. All right. Yeah, it looks like we can use it. So define the sampling distribution model and its parameters. So we know if these three things are satisfied, then the sample mean is going to be normally distributed with a certain mean and standard deviation. All right, so X bar, the sample mean, going to be normally distributed. I keep tabbing when I should be going to the previous page. What's the mean of our sampling distribution? Should be the same as the mean of the population. What was the mean of the population? Right, this right here is the population. This right here is the sampling distribution. All right. So what's the mean of the population? 125 milligrams per deciliter. And now we need the standard deviation of our sampling distribution. The standard deviation of our sampling distribution says that it should be the population standard deviation divided by the square root of our sample size. So this right here, we are population standard deviation, which is 10, divided by the square root of our sample size, which is 3. What is 10 divided by the square root of 3? We can use a calculator. You can use the slash for a fraction and SQRT with a parenthesis for a square root. We get about 5.7735. Usually 5 significant figures. Significant figures are basically how many digits are there after zeros. So if we had like this is 2 digits are after the initial zeros. This would be 2 significant figures. All right. Usually 5 is a good rule of thumb. All right, so that's our sampling distribution model. That's its parameters. Draw and label the model relative to the earlier model. Okay, so this was our earlier model. Let's draw the sampling distribution over here. So we know the sampling distribution has the same mean, right? Has the same mean, so the sampling distribution also, hold on, how do I want to do this? I wonder if I can like copy it down over here. And then we can do like one on top of the other. So that's our original, our population. And then let's look at our sampling distribution. It also has a mean of 125. But now our standard deviation's not quite 6. So over here, that used to be 1 standard deviation, but now that's almost 2 standard deviations. All right. 1 standard deviation above the mean is like over here. 2 standard deviations was like here. So this is 1 standard deviation above the mean, which is going to be like 130.7. 2 standard deviations was like right here, which is going to be like, I don't know, it's kind of hard to do this. 136.2. And then 3 standard deviations is already over here. So our standard deviations are much smaller. You could go in the other way. So it's still a normal curve. But notice what's happening. This population is much more spread out than if we only look at the average of 3. We look at 3 averages, an average of a sample of 3, we're going to get less variability. The 3 samples kind of average themselves out. there's going to be less spread to our sampling distribution. That's always going to be true in general. So yeah, it's quite possible that we look at a single glucose measurement and have it be 145. It's very, very unlikely to take an average of 3 glucose levels and have them average 145. All right. So, what is the probability that the mean of 3 measurements is at least 140? And again, for one measurement being 140 is pretty possible. 3 measurements being 140, that's much less likely. What is that probability? The probability that our average of 3 is at least 140, how can we find that? We know our average is normally distributed. How do we answer questions about probabilities of normal distributions? We use GeoGebra, which I'm not ready for. Let's see. Oh dear. Hey, there it is. Great. Good. Fantastic. And we look at normal distributions. We say the mean was 100. It wasn't 110, was it? 125. And the standard deviation was about 5.7. It was 5.7735. All right. And then this should look like our blue picture, kind of. The center's at 125. Most of the stuff is less than 140. Yeah, most of the stuff's less than 140. So what's the probability that we're at least 140? It's this small blue area, like 0.5%. Again, for a single glucose, it'd be rare to be at least 140, but not impossible. But for an average of 3 to be that big, much smaller. This is going to be about 0.0047 we found. All right, this is a very small shaded area. The probability is how much of this whole area is shaded. Very unlikely. All right. And just to put things in perspective, if we were looking only at 1, this probability would be almost 7% for a single measurement to be that big. But for 3 to be that big, it would be much, much less likely. All right, what's the 95th percentile for the average of 3 results? In other words, what average lies above 95% of other averages? And again, that's just having you remember how to do things from Unit 5. So what you'll do is you'll go over here and say, all right, we want to be above 95% of the data. You just put in a 95%, and you see that this data value right here, 134.5 about, is above 95% of the data. This is our 95th percentile. 134.4966. Milligrams per deciliter is above 95% of these averages. This is our answer. All right. Let me know if you have any questions. We got more practice. This is complicated topics. That's why these videos are longer than I normally like. But I do want to not just gloss over things. I do want to spend time explaining them to hopefully make some sense for you guys. The calculations are important, but if you can understand what's really going on, understand the concepts and how it all ties together, it's way more valuable as well. So feel free to ask questions on either the calculations or what we're actually doing, behind the scenes stuff. Anyway, I look forward to talking with you about it. Next video is more practice. So again, if you're still uncertain, don't worry, we do more. Bye-bye.